Welcome to Unit 5, Section 3.2 and 3.3, Implicit Differentiation and Inverse Functions. Implicit differentiation definitely takes quite a bit of work. Inverse functions is a little bit more intuitive, which is why there's only these 2 units in this section. But implicit differentiation definitely is going to stretch you a bit. So let's get started on that. So hopefully you remember what inverse functions are. F of g of x is x, and g of f of x is also x. That's part of the definition for an inverse function. Inverse functions are functions that are opposite of each other. So for example, if we had f of x was x plus 3, the way we'd find our inverse is we'd say y equals x plus 3. We'd swap the x and the y, and we have x equals y plus 3, or the inverse is x minus 3. So our function is x plus 3 and our inverse is x minus 3. So those would be opposite functions of each other. And if I did f of g of x, that would be f of x minus 3. I'd have x minus 3 plus 3, or just x. And you could see that that definition would work. Hopefully that was a quick review about inverse functions. So to find the derivative of an inverse, let's differentiate both sides. So the derivative of g of f of x, we're going to have to differentiate the right side of x. So we're going to use the chain rule. G prime f of x, and then f of x is my baby, so times f prime of x, and the derivative of x is 1. So g prime f of x is 1 over f prime of x. Let's put this into practice, and it will make a lot more sense. Before we practice, we're going to go over a kind of a lengthy rule for the derivatives. So let fy equal f of x and x equal g of y be inverse functions. Suppose f is differentiable in the open interval containing x naught and y naught equals f of x naught. If f prime is not equal to 0, then g is differentiable at y naught equals f of x naught. So the derivative of g of y with respect to y equals y naught is g prime of y, which is 1 over f prime of x naught. The important part here is to remember that we have to switch our x's and our y's. That's why there's an y here and an x here. So if y naught equals f of x naught and f prime of x naught does not equal 0 and it exists, then the derivative of g of y exists at y naught. Also, this statement can be used to find the derivative of g of y at y naught without knowing the formula for the inverse function, provided we know what the derivative is at x naught. The Lebesgue notation for this is dy over dx is 1 over dx over dy. So the function f of x equals x squared plus x has an inverse function of g. We want to know what g prime of 2 is. So I know that g prime of 2 is 1 over f prime of x naught, where 2 is f of x naught. So now let's solve for what x naught is. That means that 2 has to equal x to the 5th plus x. I can graph this and see where they intersect, or I can think about what squared plus itself equals 2. So one of my solutions is going to be x equals 1. So now the question is, g prime of 2 is 1 over f prime of 1. So let's keep going from here. The derivative of f of x is 5x to the 4th plus 1. Now let's find the derivative of f prime of x at 1. So 5 times 1 to the 4th plus 1, or 5 plus 1, which is 6. So g prime of 2 is 1/6. What's really awesome about this inverse function is that I was able to find this without knowing g at all. I never had to actually solve for g, which we could see would be really difficult. If I tried to solve for g first, I would have had to do x equals y to the 5th plus y, and then isolated from there. That's a pretty complicated equation. That's the power of these inverse functions. Let's take a look at example 2 on page 241. It says the function x cubed plus 2x minus 4 is 1 to 1. Let's talk about what that means 1 to 1 before we continue. That means that for every x value there is one and only one y, but it also means that for every y value there is one and only one x. Therefore, we have an inverse. In order to be able to have an inverse, the function must be 1 to 1. I know that that's a review from Algebra 2, but I just wanted to loop back and make sure that you remembered it. Find the equation of the tangent line to the graph of G at the point 8,2 on G. So we're trying to find G prime of 8, and we're going to do that by finding 1 over f prime of 2. So first let's find f prime of x. That's going to be 3x squared plus 2, and then f prime of 2 is 3 times 2 squared plus 2, so 4 times 3, 12, plus 2, 14. So g prime of 8 is 1 over 14. So there's my slope, and I have my x and my y. Y minus 2 equals 1/14 x minus 8. And of course you can simplify that and put it in any form you want, or you can just leave it as it is. Now this chart right here is definitely a chart that you're going to want to have in your notebook. This is not something we use all the time, but sometimes we do, and when we do, it's really nice to have it as a reference. Let's talk about what each of these things mean. So we have the function sine. The inverse is sine to the -1, which is often called arc sine. So the inverse function's arc sine, the derivative is 1 over the square root of 1 minus x squared. This is a really important one. We see this one all the time, arc sine. The next one is arc cosine, and that's -1 over square root of 1 minus x squared. So it's really convenient. If you can memorize this one, then you have this one just by the negative. The next one that we see all the time is the tangent. This one's also really important. We see it often. Arctan is 1 over 1 plus x squared. Notice it is the exact inverse of cotangent, -1 over 1 plus x squared. Arc cosecant and arc secant, we don't see them quite as often, but they are also a positive negative of each other. Definitely the two that we see the most that we're going to want to be able to recognize is arcsine and arctan. But copy this whole chart into your notebook, and we'll keep it as a reference for now.